Welcome to this video on solving differential equations with initial conditions. Today, we'll work through an example where we find specific values for constants in a general solution to satisfy given initial conditions. Let's look at our problem. We have a second-order differential equation, d squared y over dx squared minus d, y over dx minus 2y equals 0. We're told that the general solution to this differential equation is y of x equals c 1 times e to the negative x plus c2 times e to the 2x. Here, c1 and c2 are constants that we need to determine based on initial conditions. Our initial conditions are y of 0 equals 2, and the derivative of y with respect to x at x equals 0 is negative 3. To use these initial conditions, we first need to find the derivative of our general solution. The derivative of y with respect to x is negative c 1 times e to the negative x plus 2 times c2 times e to the 2x. Now, let's apply our initial conditions. First, y of 0 equals 2. Substituting x equals 0 into our general solution. Y of 0 equals c 1 times e to the negative 0 plus c2 times e to the 2 times 0. Since e to the 0 is 1, this simplifies to c1 plus c2 equals 2. Next, let's use our second initial condition. The derivative at x equals 0 is negative 3. Substituting x equals 0 into our derivative, y prime of 0 equals negative c 1 times e to the negative 0 plus 2c2 times e to the 2 times 0. This simplifies to negative c1 plus 2c2 equals negative 3. Now, we have a system of two equations with two unknowns. Equation 1, c1 plus c2 equals 2. Equation 2, negative c1 plus 2c2 equals negative 3. Let's visualize this system of equations. The blue line represents c1 plus c2 equals 2, and the red line represents negative c1 plus 2c2 equals negative 3. The solution to our system is the intersection point of these two lines. Let's solve the system algebraically. We'll add the two equations to eliminate c1. c1 plus c2 plus negative c1 plus 2c2 equals 2 plus negative 3. The c1 terms cancel out, giving us 3c2 equals negative 1. Dividing both sides by 3, we get c2 equals negative 1/3. Now that we know c2 equals negative 1/3, we can find c1 using our first equation. c1 plus negative 1/3 equals 2. Solving for c1. c1 equals 2 plus 1/3, which equals 7/3. Therefore, our final values are c1 equals 7/3 and c2 equals negative 1/3. Substituting these values into our general solution, we get the particular solution that satisfies our initial conditions. Y of x equals 7/3 times e to the negative x minus 1/3 times e to the 2x. Let's visualize this solution. The blue curve shows our particular solution, y of x. Notice that at x equals 0, the function value is 2, and the slope at that point is negative 3, confirming that our solution satisfies the initial conditions. In summary, we've solved a second-order differential equation with initial conditions. We found that c1 equals 7/3 and c2 equals negative 1/3, which gives us the particular solution that satisfies both y of 0 equals 2 and y prime of 0 equals negative 3. This method of using initial conditions to find specific values for constants in a general solution is a fundamental technique in differential equations.